Just as we can't give a numerical value to an expression like x plus 2 until we choose a value for x, we can't give a truth value to a well-formed formula like P and Q implies R until we've chosen truth values for the propositional variables P, Q and R. But even once we've done that, it's not quite clear exactly how we should go about assigning truth values to well-formed formulas made out of those propositional variables. And that's going to be the subject of our next 2 lectures. So we'll begin with how we assign truth values to propositional variables. We do that with a truth assignment, which is simply a function from the set of propositional variables that we're interested in to the set true or false. For example, if you had a set of propositional variables which just consisted of P and Q, then a truth assignment could be a function alpha such that alpha of P is true and alpha of Q is false. So once we have a truth assignment, we'd like then to extend the truth assignment so that it gives truth values for well-formed formulas, even complicated well-formed formulas. And to do that, we've got to make some sort of definition about how we're going to do that. And we'll begin by thinking about the simplest well-formed formulas which are not just propositional variables on their own. That is, the well-formed formulas that only have one connective, like P or Q, where the connective is or P implies Q, where the connective is implies. And what we'll do is we'll define the truth value of those well-formed formulas to be a function of the truth values which our truth assignment gives to the propositional variables in those formulas. And we'll do it by writing down a truth table. So the meaning of a truth table like this is that when you have a truth assignment which gives the value true to P and true to Q, then we'll extend that truth assignment to the well-formed formula brackets P and Q by saying that it assigns P and Q the value true. And similarly, if we have a truth assignment that makes P true and Q false, then looking at the second row of the truth table, what it tells you is that the way we will extend that truth assignment to the well-formed formula P and Q is by making P and Q false. So we choose this definition because it captures the standard mathematical logical usage of the word and. If you say, it is Tuesday and it is raining, then you're telling the truth, you're giving a true statement, if and only if it is Tuesday is true, and it is raining is true. So both of the two substatements must be true in order for your compound statement made with the word and to be true as well. And that's what our truth table captures. You can see it only gives the value true to the well-formed formula P and Q if you've got a truth assignment which makes both P and Q true. So we need truth tables for the other logical connectives as well, and here they are. These are the definitions of the truth tables for the other 3 connectives. There is the truth table for P or Q, and you can see it behaves in the way which you expect the word or to behave intuitively. And here is the truth table for not, and again, it captures just the normal way in which we use not when we're talking mathematically or logically. The only truth table which tends to cause a little bit of controversy, or people tend to find unintuitive, is the one for implies. And here is that truth table for implies. So the bit of this truth table which people tend to find confusing is these bottom 2 rows where P takes the value false. So when P is false, what you can see is that regardless of the truth value of Q, we're always going to regard the statement P implies Q to be true. So whenever you have a truth assignment which assigns P the value false, it will assign the statement P implies Q to be true. So if you think about this and you don't like it, well, you have 2 options. One of which is just to regard this as a definition and say, okay, well, I accept that this is the definition of how we extend truth assignments to propositional variables to truth assignments on well-formed formulas P implies Q. And another is to adopt the idea that you're going to regard P implies Q to be false only when you have an explicit counterexample to it. So that's why I think this is a reasonable definition. The only way you can have a counterexample to saying one thing implies another is if the first thing was true but the second thing is false. And that's exactly when we give the value false to the well-formed formula P implies Q. We give it the value false only when P was true but Q was false. So this principle that we only give the well-formed formula P implies Q the value false when we've got a counterexample to P implying Q is, I think, a good justification for our choice of truth table here. If you'd like to see a bit more in-depth discussion of why we use this truth table, you can look at the online notes for this lecture, where you'll find a link to an interesting article about why we use the truth table that we do for implies.